Episode 15 of the World of FPGA podcast. To start up an Xilinx Zynq SoC, many steps are required. To get an overview, we will talk today about Bootloader. Welcome to the World of FPGA podcast. I'm your host, David Kirchner, and I will lead you through the world of FPGA. And now, let's begin. Hello and welcome back to the SoC world of Xilinx. We have talked in the last time often about SoCs, about developing software, about debugging software, and today I will give you an overview how the Zynq 7000 is starting up. That's the idea of this episode, and that's because of an FPGA is not configured as start. If we power up our device, there are special flash-based device FPGAs, but here in the Xilinx world we have our SRAM-based devices. So if you power it up, there's nothing programmed, there's nothing configured. The FPGA is blank, the Zynq core, the ARM core in the Zynq isn't running. So we need some mechanism inside of this FPGA, of this Zynq, that starts the process of programming the bitstream of starting software. And in this episode we will look now into the Xilinx Zynq, and we have here many different stages of booting. And as an idea, let's think about an embedded system with a Linux operating system, and we start now after powering up and after reset. The first stage is the stage 0 boot. It is also known as the BootROM. The code of the BootROM is inside the Zynq programmable system. Programmable system, that's are the ARM cores, or in short, we have our PS. The code is started direct after the reset is released. The core reads the boot configuration from the MIO pins, because we can have different devices to boot from. We can boot from an SD card, we can boot from flash memory, we can say that the system should remain in JTAG. So this is the first point where the MIO pins are read, and the BootROM now searches for a valid header. And if it found a valid header, it will load the code into the OCM, this is the on-chip memory inside of the Zynq, and then it starts directly from this memory the code, and it jumps into the next stage. So this is stage 0. Stage the BootROM is controlling the first steps of a Zynq. The next stage is the first stage bootloader. In short, it is called FSBL, and FSBL is often read if you are working with Xilinx Zynq. So it is known, and it's an abbreviation for the first stage bootloader. The BootROM has loaded the first stage bootloader in the stage 0 into the OCM, and this code you will generate it while you are creating your FPGA project. So you have to generate the FSBL code, but it is mostly more or less automatically done by your development system. So Xilinx is generating a code for your specific design, because it initializes all the needed components in the SoC. So you will have some settings for your memory clock, or for your CPU clock, or for the clock in the PL. So you need this all the information from your project, and this goes into the FSBL, and on startup it just will initialize all the components. After that, the FSBL searches for a valid structure on the different boot devices. It also uses the MIO pins to read the boot configuration, and then it searches for a special valid structure. And if it found it, the FSBL loaded the bitstream into the PL. That's done by the FSBL, and it will load the second stage bootloader into the memory. All the three things, the FSBL, the bitstream, and the second stage bootloader, are packed together in, for example, one file or in one block in the memory, in the flash memory. And that's because the FSBL knows all the correct places for example, in the flash. And that's because it's the function of the FSBL to load the bitstream and to load the second stage bootloader. And after that, well, it's just hands over to the code of the second stage bootloader. And now we are here in the second stage bootloader. Well, here we can also have our bare metal application or another more complex bootloader. That's the two things we can have here on the second stage. And if we have an embedded system, and in this case an embedded Linux system, we are most time using U-boot. U-boot is very well known in embedded systems. It is very powerful because it just can also access Ethernet, it can access USB, it can access the SD cards, MMC memory, and flash memory, and so on. And all the information where to load the system from are saved in an environment in many variables. And that's because of that, the U-boot is very, very flexible, and you can just create your own boot scripts and configure the Linux kernel from this point and so on. So we can, because it is so flexible, we can just decide now what we want to load and from where we want to load. So we can load Linux now from an USB stick or from Ethernet or from SD card. So U-boot loads the kernel and maybe also the file system. If you have a RAM-based file system, it also can load the file system into the RAM, and then it hands over to the kernel. And now we are on the stage, we have our Linux kernel, and it is the time for our kernel now, and it starts all the drivers and the drivers and the device detection, that's correct, and it's doing some background things, and then it tries to find a file system, try to mount the file system, and after that it will start the init process, so if you decided to do so. And after that we have our init process, which is the base of our system. Our system can now boot, and the init process will start our applications and our background daemons and so on. So that's the last step here in the boot up of a system. So let's wrap up. We can booting an embedded system on a Zynq with many different boot stages. We have in every stage special functionalities, and every stage is needed for our start of our system. But if you want to be more flexible, well, you can just design your boot procedure on your own. It's also possible to rewrite the FSBL to change things there, because we have the source code from Xilinx in the Vitis projects. So you can just modify this, and later on you can boot your own software. And that's all for today. I hope it helps a little bit to understand how the Zynq is starting up. And many other SoCs will also work the same way. And I guess you can now easily transfer this knowledge to other devices. In the next episode, I tell you something about my visit on the FPGA conference in Munich, and after that we will go a little deeper into debugging SoCs. All links and further information can be found at world-of-fpga.com/WFP015. If you found this episode helpful, please rate it on Apple Podcasts and share it with your colleagues and friends. That's the end of today's podcast episode. Thank you for listening and for your attention. So I say goodbye, here next time, your David Kirchner.